Good morning, good afternoon, good evening, everyone. Welcome to today's Earth session by WEkEO, focusing on natural disasters. I'm Marine Delorme, Training and Capacity Development Officer at Mercator Ocean, and I'll be guiding you through this webinar. Today, we're diving into the WEkEO platform, what it is, the powerful data and tools it offers, and how you can use them. By the end of this session, you'll not only understand the key features of WEkEO, but also see practical examples of how these tools can be used to monitor and respond to natural disasters. So let's get started. Before we begin, let's quickly go over some house rules to make sure you enjoy this session to the fullest. Please don't use the chat box on your right-hand side for questions. It's there for greetings and for sharing links with participants throughout the session. If you have a technical or content-related question, we invite you to use the dedicated Q&A section. You can scan this QR code or click the Q&A button at the top of your screen to ask questions to our speakers. We'll have a Q&A session at the end of each presentation. And while you're there, you'll also see a quick survey about today's webinar. Feel free to fill it out anytime during the session. We will also send you the survey link after the webinar, so you can fill it in later if you prefer. Finally, we encourage you to visit the guidelines and resources section on the event website. There you will find useful links to help center articles and several interesting and relevant parts of the WEkEO website, and tools like use cases and additional tutorials. And now I will leave the floor to the second moderator of today's session, who's Daria Andreevskaya from Noveltis. Daria, are you there?
Yes. Hello.
Hi.
And thank you, Marine, for the presentation. So yeah, my name is Daria Andreevskaya. I'm from Noveltis, and I'll be your second moderator for today. And I'll be here just quickly present you the agenda for today. So first, we will start with an introduction to WEkEO service by Marine, who you already know. Then we'll move to the presentation of WEkEO Dask Gateway by Anna-Lena Erdmann, who is a data services and analytics expert in EUMETSAT. Then Anumaya Sandstrom from EUMETSAT as well will talk about fire hotspots and smoke monitoring with Sentinel-3. And next, we will move to the user testimony for today, which is a use case of 2020 Lake Victoria floods presented by Rosa Pietro-Justi, who is a PhD candidate and in the Free University of Brussels. And the last presentation for today is going to be by Ben Loveday, who is a marine earth observation expert from EUMETSAT as well. And he will talk about visualizing tropical cyclones impacts using altimetry. And the last closing remarks, Marine will come back and tell you some more information. And well, now we move on to introduction to WEkEO and Copernicus by Marine. And Marine, the floor is yours.
Thank you, Daria. So the Copernicus is the Earth observation component of the European Union space program, and its main goal is to monitor our planet and the environment around us. Copernicus provides free and open access to a wide range of information services. These services are built on satellite observations combined with in-situ data collected on the ground, at sea, and in the atmosphere. This information supports service providers, public authorities, and organizations in making better decisions and ultimately improving the quality of life in Europe and worldwide. The information is delivered through dedicated portals designed to meet the needs of different user communities. Copernicus offers a huge amount of environmental data across its different services, and WEkEO brings all of this together in one single platform. Instead of navigating multiple portals, you can access original data from all Copernicus services and Sentinel missions directly in one place. Whether you're working with marine, land, atmosphere, or climate data, everything is available in a unified environment. In January 2025, WEkEO launched a fully revamped website with a new visual identity and a more intuitive, responsive interface, making navigation much smoother. New features were also introduced to help you work with data more efficiently. Through wekeo.copernicus.eu, you can explore the data catalog, use cloud computing tools, access training materials and use cases, and join events. The data is free and open. You just need a simple registration to download or process it. Getting started with WEkEO is very simple. You can explore and browse the available data without any registration. Everything is openly accessible. By creating a free account, you unlock additional features such as personal workspace, cloud-based processing tools, and advanced computing services for more complex analysis. The platform gives you free access to the full range of Copernicus environmental data, along with a cloud environment that allows you to analyze datasets directly online with no local setup needed. You'll also find dedicated user support and a comprehensive library of training materials, including Jupyter and R notebooks to help you develop your skills. For larger scale or operational projects requiring additional computing power, commercial cloud options are also available. WEkEO gives you access to over 400 datasets from Sentinel missions and the Copernicus atmosphere, climate, land, and ocean services. To help you explore this data, two tools are available: the Expert Data Viewer, which provides a detailed interface for dataset visualization, and the Light Data Viewer, designed for faster and simpler visualizations. We'll explore both tools in more details during day 2 of this training session. WEkEO also offers a Jupyter Notebook gallery with over 100 ready-to-use notebooks developed across the Copernicus services. You can view notebooks directly, clone them via GitLab, or customize for your needs, or launch them in the WEkEO Jupyter Hub if you're a registered user. This growing collection of notebooks covers a range of topics and workflows to help you learn and apply best practices when working with Copernicus data. The WEkEO workspace, which was called WEkEO Jupyter Hub before, goes beyond just Jupyter notebooks. It offers full Jupyter Lab environment where you can explore data, perform basic analysis, and follow interactive workflows. It's suitable for everyone, from beginners to advanced users, and includes access to Jupyter Lab, RStudio, and the Xcube viewer for visualizing data cubes. Access requires a registered WEkEO account, which is completely free, obviously. The WEkEO Drive provides registered users with secure online storage to save, manage, and share their work directly within the platform. This feature supports seamless collaboration and easy access to files used or generated in the WEkEO workspace. WEkEO also provides advanced tools designed to help you work more efficiently, especially when dealing with large datasets or complex analysis. One key component is the Harmonized Data Access, or HDA API, which gives you unified access to original Copernicus data across all services. It allows you to automate data retrieval and efficiently handle large volumes of data without switching between platforms. WEkEO also integrates with plugins such as Climate Lab and EarthKit, which simplify data handling by automatically loading datasets into Python-ready formats like Xarray. This means you can focus directly on your analysis, particularly in data science or machine learning workflows, for example. Finally, EO Canvas enables serverless, cloud-based pre-processing directly where the data is stored. By processing data closer to the source, you reduce download sizes and speed up your overall workflow. For users with more advanced processing needs, WEkEO provides scalable cloud computing resources to support both research and operational activities. Through the Innovation Lab, you can apply for free cloud access by submitting a project proposal. If selected, you'll receive computing resources suitable for prototyping, testing workflows, and research projects. A great way to develop and validate ideas at no cost. For larger scale or production level requirements, WEkEO also offers commercial cloud and high-performance computing solutions. These include configurable virtual machines and access to a leading European HPC environment designed to handle complex and high-volume data processing tasks efficiently. Last but not least, WEkEO offers dedicated expert support to help you make the most of the platform. Whether you're just getting started or tackling more advanced tasks, you'll find a comprehensive help center with detailed articles covering a wide range of topics. You can also get instant assistance by asking a question to our AI agent Neo or chat directly with a member of the support team through the live chat widget. It's easily accessible at the bottom right corner of every page on the website. So that's it for the introduction to Copernicus and WEkEO. A number of links were shared directly in the chat on the event website, so don't hesitate to have a look at these later on. And so we will now go to the next presentation, which is from Annalena Erdmann, who's a data services and analytics expert at UNSAT. And Annalena is going to talk to us about the WEkEO Dask gateway. Annalena, are you here?
Yes, I'm here.
Great.
Thank you for
I'll
the
stop
introduction, Marine. I'll share my screen and I hope you can see it well. I'm gonna share with you some details about a new service we've launched like just really recently on the WEkEO workspace. So it's a component of the WEkEO Jupyter Hub environment, and that is the Dask gateway. It's going to be a bit of a technical presentation, maybe also a bit more for the advanced users here in the audience. But nevertheless, what I would like to what I'd like to show you is that in case you are facing some of the issues I'm going to present just in a second, you maybe just remember back to this presentation and just remember that there is a solution for many issues when you process Earth observation data. So my presentation is the Dask gateway on the WEkEO workspace. What is it, why, and how? Let's start with the what is it. In case you've never heard about Dask or Dask Gateway before, it is a flexible parallel computing library for Python that enables you to scale your data analysis workflows from your laptop to large clusters. So what does that actually mean? It means that you can process large amounts of data in parallel, depending on how many resources you have, how many workers you have working on your data. And yeah, I think it goes without saying that things just go faster when you do processes in parallel, because you don't have to do them one after another, but in the same time, you can do so much more. Also, Dask includes lazy evaluation. That means you don't need to compute everything right away, but you can wait until you do the actual processing. And also it is compatible with your hopefully favorite Python packages for Earth observation analysis, for example, Pandas, NumPy, Xarray, Rio Xarray. So if you have workflows using those packages and many more already, then moving to Dask for you might not be that big of an issue. It's also very memory efficient. That is especially relevant for Earth observation data when you process large amounts of data. And yeah, you can scale your processing from laptops to clusters. So you can start very small and then scale up to large computational resources once your project is more mature. A bit of so why should you worry about Dask, or why should you even look at that? Let me tell you a story about Ivar. He's a university student and he wants to do a project with Sentinel-2 data. Just some simple processing, maybe some land use classification and so on. So what he does, he takes his laptop and he downloads a couple of Sentinel-2 files, and then he tries to process them. And then he gets this very scary error, which you can see here in the middle, which means that the kernel died. Maybe some of you have already gotten those error. For me, it always gives me shivers because it means something is either wrong with my code or my computer is just not powerful enough for the data I want to process. This is then a situation where you can use Dask to lazy load data so that it doesn't exceed the resources of your machine. You can do the process in parallel. You can process things after another. You don't have to do everything at once. And this is what Dask do, and that is what Dask on the WEkEO workspace can do for you. So remember, if you ever run into an error that your kernel is dying, maybe Dask could help you solve this issue. Another person, Mary, she is preparing a large project to process Earth observation data for the whole world, which can include multiple terabytes of data, so large and large amounts of data. So her approach is to start very small, like with one country, for example, Germany, or maybe even a state in that country, and then scales up to the processing later. In case you plan something like this, Dask can also help you to scale up the code so that she can start out very small on her computer with one country or one state, and then later, when she's really sure about her approach, about her project, about like what algorithms she wants to run, she can go, for example, apply for the WEkEO Innovation Lab to get some more computational resources, or maybe get the computational resources from her university or from her employer, and then scale up that processing to the whole world with way more resources. So in case you ever face such a situation, just remember, Dask could help you with that to make your code ready. So to sum that up very briefly, so you can use Dask to process datasets larger than your memory available. So for example, large satellite tiles, which you find in the Sentinel datasets, or also lots of, for example, data from Sentinel-1 or Sentinel-2, but also data from Sentinel-3 can become very large. You can scale up from your laptop to the cloud or HPC using Dask. So that is the use case when you start small, but you already know, okay, in the future, I want to go big. And then you can accelerate analysis with parallel computing. So saving time by not doing every computational process one after another, but for parallelizing them. So we do have a Dask gateway on the WEkEO workspace. You can access that through the portal when you go to the WEkEO workspace, or you can just use this link. It is available in every server profile, so it doesn't matter if you select Earth observation, machine learning, or the machine learning GPU, you can utilize the Dask gateway in any of those servers. We do have the following resources, so you can have a maximum of 2 clusters per user. So always remember to close your cluster once you're done. We have 1 gigabyte of memory per worker and a maximum of 3 workers per cluster. I will show you in a second what this exactly means. If you're already experienced a bit with large Earth observation data processing, these resources might seem a bit limited. So the idea behind the Dask gateway on the WEkEO workspace is to really enable you to try out Dask to make your code Dask ready. And then once you're ready, once you're comfortable with your algorithm and so on, so that you can go to a larger Dask cluster, for example, through the WEkEO Innovation Lab or through your own computational resources to then really scale up the process. So prototyping with Dask on WEkEO, and then move to a larger computational infrastructure. So now I'm going to show you very briefly on how you can use the Dask gateway on the WEkEO workspace. There are two ways of using the Dask gateway. One is via code, which I'm going to show you in a notebook. And then you can also use the graphical user interface. We might not have time for that today, but there will be many resources available online to show you how this is done. I will share my Jupyter notebook, which I hope you can see now.
Yes, we can.
Yeah, okay, super. This will be available also in the WEkEO Jupyter Hub throughout this week. I'm happy to then update the presentation with the link so that each of you can really access this notebook and try it out for yourself. So it starts a bit with the introduction. I've said most of that already. You can just revise it later. Also when Dask is useful, when Dask might not be useful. And yeah, this graph here, I want to spend a few words on this one. So because it's important to understand how Dask works. So for this parallelization of processing, you have like the workers. And the workers are really you can imagine this as the people who do the work, okay? And then you have the scheduler, who is more or less maybe the manager, like distributing the work to the workers. And then you have your notebook, which defines the scheduler and the worker. You can like say how many workers you want, maximum 3, and how many like resources are allocated to each worker. We're first going to start with importing the libraries. So if you see the Dask gateway is the main library here, and we are using like the other Xarray, NumPy libraries. You might be familiar with that. And then we create the gateway connection. So it's important that you run this notebook on the WEkEO Jupyter Hub, because otherwise this will fail already. Then we can get the cluster options. So as I said, we have the workers, which we can set. We have the worker memory, which we can set as well. Either here in this graphical interface, or you can just use the code. So we can scale the cluster, so giving it more workers, giving it less workers. And then finally, we can see where it is located, so to say. The dashboard is a very, very interesting thing as well, because there you can really see what is going on in the background. So you see, for example, here you have your 2 workers, which we just set as options for the clusters. And currently the workers, they're not doing anything because we have not computed anything yet. And now we can start with the computation. I'm just creating some dummy data for the sake of this demo. And then let's do a mean over time. That was very fast now, because it's currently, you can see it's a lazy operation. So at the moment, we see that we want to take a mean of the data, but it's not computed yet. So you see it was very, very fast. And now we trigger the execution. This will take a while. And we now see that there is something happening. Okay, the 2 workers, they are working, and they are doing different things at different times. And this is how the scheduler orchestrates the different processing steps. So you have at the moment 2 threads working on your processing at the same time. The same also works with X-array. So you can work with Dask and X-array pretty seamlessly. This is an X-array data set I have here now. And using this compute functions, we can trigger the Dask gateway. And you see, it was very fast, but the dashboard changed. And when you have like larger processes which take longer, you will see a bit more here in this dashboard. Okay, then you can scale your cluster at any time, scale it up, scale it down, monitor what is currently allocated, and then in the end, as you might recall what I said in the beginning, per user you can only have 2 Dask clusters, so always remember to close it when you're done, to free up the space for your next cluster, but also for the other users. Good, and that is it for the demo. I have put together some resources where you can learn more about the Dask Gateway. I will add links to the notebook and to some help desk articles on WEkEO to this slide. But as I said, it's a very recent development, and now you just see how recent it is because you were the first ones to see that notebook before it was published. That was it from my side. You can always contact the WEkEO user support for any questions or specific questions. You might as well contact me also about the Innovation Lab, how to really get more resources. And I'm happy to take any questions also now.
Thank you, Annalena. I don't think we've received any question for now about the presentation you just gave, so it must have been super clear. So thank you very much for this.
Okay, thank you.
I don't see any incoming question. We just have some comments saying this is very interesting. So thank you for presenting this very new tool. And no question coming. So I guess this is it. So thank you again for your participation. And I guess we'll see you soon.
Thank you. See you.
Bye. Okay. So we will now go to the next presenter, who is who is Anumaya Sundström from UMETSAT, and Anumaya will give a presentation about fire hotspots and smoke monitoring with Sentinel-3. Anumaya, I can see you. Can you hear me?
Yes, I can hear you.
Hi, I'll stop
Hello.
sharing my screen and you can start whenever you want.
Yes, thank you. So I will share my screen and start the presentation. So, good day, good morning, evening, afternoon also from my behalf. My name is Anumaya Sundström, and I am an atmospheric scientist working at the Finnish Meteorological Institute, and I will give this presentation now on behalf of UMETSAT. So I'm working also in a project for the UMETSAT. And as it was already introduced, so my topic today is about monitoring fire hotspots and smoke using Sentinel-3 satellite. This is the basic concept and some kind of a theoretical background for this topic. And on Thursday, 26th, then you will have my colleague Noemi Fazzini, who will give a really hands-on presentation how to really use this data that I'm now presenting. So this is going to be a little bit like a theoretical background, how the fire events can be monitored using satellites. So as you already might know, so wildfires are happening across many parts of the world. in some parts of the world, the wildfires are really essential part of the natural biological cycle of the region. But with the drying and warming climate, there is also an increasing number of fires occurring in places where we really don't want them to occur, so which can cause really a lot of destruction for the people living in the area and causing a huge problems in air quality. Satellites are a very good way to monitor these fire events because satellites can give you a very broad and near real-time view on what is really happening. If you think of yourself looking at large fires from ground, so you might see one or two fires, but you really maybe cannot understand the extent of the real event. But when you look at the situation from space or from above, so then you can get the much more clearer view on how extensive and what kind of situation and how large area this fire events can affect. So with satellites, we can observe many aspects of the fires. First of all, we can monitor the active fires, so where the fires are occurring and how intense they are. Then we can also do some land cover remote sensing, so then we can assess how much areas were burned and damaged. But then we also can look at the atmospheric emissions and how much, for example, smoke is coming from the fires. And as I said already, so the satellites provide a really broader view of these very extensive events, and they can be supporting early warning systems, also air quality forecasting and monitoring, and also then they are in growing numbers nowadays used for the emergency response activities. My presentation and also the hands-on exercises on Thursday will cover the Copernicus Sentinel-3 satellite. Currently, there are 2 operational Sentinel-3 satellites carrying exactly the same instruments. So the A and B satellite, so the A was launched in 2016 and B was launched in 2018. And these both satellites are flying and orbiting the Earth from pole to pole, so they are in a so-called polar orbit at about 800 kilometers height. And the overpass time of these satellites is about 10 local time, or then 10 in the evening local time. So this means that every day you will get an observation from these satellites over your area at about the same time. EUMETSAT provides many products from these Sentinel-2 instruments. They provide a lot of marine data, but for the fire monitoring, especially important data are the near real-time aerosol optical depth and then the near real-time active fire observations, which I will then talk in more detail today. So the Sentinel-3 satellites carry multiple instruments, and for fire monitoring, the most important instruments are this ocean and land color instruments, so-called OLCI instrument, and then the sea and land surface temperature radiometer, so SLSDR. And today, actually, then I will cover the observations from the SLSDR instrument mostly. So here is a kind of on a one page, just a kind of a broader view, what kind of information you really get from the Sentinel-3 instruments. So first of all, there is this OLCI true color RGB images where you can already visually see now by not knowing anything about fire monitoring and satellites, so you can clearly guess where the fires in this case are. But then when we go a little bit further in the observation, so we kind of extend and retrieve additional info from the SLSDR instrument, so we can get the fire radiative power, which actually shows us the real location of active fires, and then it gives us also the indication of the intensity of the fires. And then we have the aerosol optical depth, which is really related to the amount of smoke. So about the SLSTR instrument, I am not going to talk really in very detail about the instrument here, but what I want to say is that from this one instrument, we can actually get information both on the aerosols and also on the active fires. And this has to do with the fact that the instrument is actually measuring so broad spectrum of the radiation. So the SLSTR instrument is measuring the radiation that is originating from the sun, so at visible wavelengths. Then it's observing radiation at near infrared wavelengths, and then it is also observing radiation from the thermal infrared. And by putting all this information together, so we can then retrieve information on the smoke aerosols, which is related to the aerosol optical depth parameter, and then also the active fire observations, which are related to the fire radiative power. To give a very, very short and simplified explanation what the fire radiative power is from satellites, so I'm explaining it only with this one slide. So actually the FRB, so FRB is telling us how fast fire is releasing energy. So it is kind of like showing us the intensity of the fires. The unit is normally given as megawatts, and the higher the number, so the higher the FRP is, so then the more intense the fire is. And this information can be obtained when we now use the radiation information from the near infrared and thermal infrared channels. So we are basically measuring how hot some object is. And the basic idea for this whole FRP, yet this is really simplified explanation now, but basically the satellite is observing hot objects from the surface. So basic idea is that when you have a fire on the ground, so that area appears hotter than its surrounding areas that where you don't have the fire. And this is the basic idea behind observing these hot objects and FRP. This is a little bit like when you go more in detail to the theory. So the FRP is a little bit more complex than this, but this is just like now giving you a very short, let's say, overview and idea what this FRP is about. And there you can see on a map now over one day, so you can see an example how these FRP observations can look like. And here I might also say that the satellite, it really exactly measures the hot objects. And hot objects are not always fires, so sometimes also some volcanoes and industrial facilities can appear in these maps as a kind of fire hotspots. But those then observations you can separate from real fires, so that if you look at multiple days in a row and the fire is always happening at the same location, then you might think that it is maybe not a real fire, but some other hot object. Last summer, there were very intense fires happening in the Iberian Peninsula, especially in August and mid-August. And here I have now an observation of the Sentinel-3 SLSTR FRP. This is maybe one of the most intense fire days, 15th of August. And I have combined here the observations from the SLSTR instrument, both from the Sentinel-3A and B satellites. And you can see here that the locations of fires are shown. And when you, for example, then combine this information with the RGB, so you can very clearly see how these fire hotspots really then match with those smoke plumes that you can see also visually with your own eyes. Then if we move from the active fires to the atmospheric emissions, so one of the most intense emissions that the fires are always producing are the smoke emissions. So the smoke that you can visually also see with your eyes. And that is also quite often the most hazardous emissions also from the fire, so can cause a lot of, for example, breathing problems. And for this, we can get the aerosol optical depth, and sometimes this is also referred aerosol optical thickness, so AOD or AOT, this is the same thing. And basically, this parameter tells us how much sunlight is reduced by the particles in the air. So basically, at the visible wavelength, so the radiation from the sun is entering the atmosphere, traveling through the atmosphere to the Earth's surface, and then going again back through the atmosphere. And during this trip, so the radiation is reduced by the aerosol particles in the air. And the more we have aerosol particles in the air, the more the radiation is reduced. So this is basically the AOD is therefore related to the amount of aerosols in the entire atmospheric column. The AOD itself tells us information on any aerosol. So just based on the AOD value alone, we cannot say whether it's smoke or not. So we don't have the information what type of aerosols is causing this reduction in the radiation. From satellites, the AOD is typically retrieved using the visible wavelengths, and the satellites cannot provide the AOD value when you have cloudy skies, snow on the ground, or then the sunlight is too low. And from the Sentinel-3, so you can really get the near real-time AOD at the 550 nanometers wavelength. And the AOD is really just a number. So this is a little bit like a difficult parameter to turn into a real life, let's say, example. So this is just a unitless number that varies from 0.05 up to 2 or even up to 4. And I have just listed here on the slide some thresholds based on my long experience working with this parameter. So this is just my personal thresholds. There are no generally agreed thresholds, what is low and what is high, but you can say that when you have the AOD, for example, exceeding 0.5, so that can be considered then as a high AOD. And there you can see the map for one day, the AOD obtained from the Sentinel-3 satellite. I already mentioned that the AOD cannot be retrieved over areas where you have clouds, so that's why you have a lot of holes in the data. Also in the northern areas, so for example, I'm here in Finland, so we have during the winter time, we have missing observations because of there is not enough sunlight here. And sometimes also in cases where we have very thick aerosol plume, so then actually the retrieval algorithm can interpret that as a cloud and not as aerosols, and then we also might have some missing observations due to that. And now I'm coming almost to the end of my presentation, so I'm just showing here now the FRP and the AOD maps together, because what I said is that just based on the AOD values, you cannot say where the smoke is. But when you combine this AOD information now with the FRP observations, and I have circled here some areas where we see elevated AOD, and when these elevated AODs matches with the area also with the high intensity of fire, so then we can kind of conclude that these aerosols are most probably the smoke aerosols. But you can also see here in the AOD map, you can also see areas where you don't have any FRP observations, so then it means that the aerosols are some other type and not smoke. And here is an example from the 15th of August in the Iberian Peninsula, where we had actually really high AOD values originating and really a lot of smoke originating from these intense fires. And this is again the exercises that then you will be having the presentation on Thursday with Noemi. So this was my presentation. Thank you.
Thank you very much, Anu-Maija. We received some questions for you from participants, so I will share my screen. Okay, so you should see my screen now. The first question we got was, is there a tool to determine whether the Copernicus satellite will pass over a specific location? What is the delay in the data capture to the data access or availability?
Yes, so I think there are tools to determine the both Sentinel satellites. If you combine the A and B, so there should be like overpass every day. So it is mainly has to do also with the conditions. So whether you have a lot of clouds, if you considering the aerosol observations. With the fires, so the some very thick cloudiness can also then prevent some of the observations, but mostly you should have almost daily overpass over your location with these satellites combined. But it is then mainly due to the local conditions, whether you can see anything or not. The delay in the data capture, so I think the near real time is about, we are talking about some hours of the satellite overpass when it's then processed as these parameters.
Okay, thank you very much. Next question is, how have you addressed challenges with limited observations due to aerosols predictive tools?
Well, that is something that we will just need to. That's the reality that we need to always live with. So quite often in my like research work, so how I approach these things, that if we have like I will combine data from satellites. I will combine data from models, for example, from comms. I will combine data from in situ observations. So quite often it can be that the satellites are not giving you maybe because of the conditions, for example. So you will have missing observations, and then you might to kind of complement these observations from different sources. So that is the one way to take it.
Okay, thank you. Next question is, what is the satellite resolution for the tools of FRP and the other in degrees or kilometers?
So the satellites, the FRP observation is given as a kind of a point. So it is a point data. So when you are then handling on Thursday the satellite data, so it is a point, let's say point information. So it will have the latitude and longitude of the FRP observation. So it is not in a gridded format. But in generally, so FRP observations, there can be like 100 meters, hundreds of meters resolution, spatial resolution, or even with some instruments, even tens of meters. But if you have, let's say, like a campfire, like a like a half a meter campfire, so satellite cannot see that. So that's there is also some limitations due to the spatial resolution. So how much you can measure from 800 kilometers above.
Okay, thank you. Next question is how to disregard the static heat signals from industrial operations.
So the best way is that first of all, if you look at the FRP observations, let's say 1 month in a row, and if you see that every day or every second day there is the same observation, exactly the same location, and it doesn't move anywhere, so then you are pretty sure that it's coming from the industrial operations. In some other FRP products, there is also some predefined sources that you can flag if it is a natural fire or then if it's an industrial fire. But the basic rule is that if you see like a very static signal coming from every day from the same location, and then if you maybe take a map or look what's there, and you see that there is some industrial facility, so then you are pretty sure that it's really an industrial signal.
Okay, makes sense. Next question, is there any way we can get some other details about fire, like rate of spread or intensity?
Yes, so the FRP is the intensity. So that tells you how intense the fire is. So you can directly link the FRP to the intensity of the fires. There are also other satellite products that can be like when you are analyzing the fire. So there are other products like the fire perimeter and the burn scar and all these kind of things that then when you can do using the satellite data some kind of post assessing of the fire. So how much did it burn and so on. And there is also a lot of also EUMETSAT actually material for this kind of EUMETSAT material. So maybe we can also link that our material from the EUMETSAT and fire guides for this session then, so that people can find out what really how wide, how many things you can actually see from the satellites and study the fires.
Yeah, absolutely. We can make this link available. We'll just take one last question. We actually received a lot of questions from you, for you, Anumaya. So what we'll do with the questions we don't have time to answer now is we'll send them to you, Anumaya, to answer. And we'll then share a post-event report with participants with answers to the questions we haven't had time to go through today. So I guess the last question we'll answer now is, can you use the tools to determine hotspots before the fire start, or just the spots where the fire has already started?
So this is basically because the satellite is observing only the hotspots. So when the kind of, I think you can see only when the fire has been ignited. But then we have when, for example, it is also explained in the EUMETSAT fire guide, but then you have some parameters from satellites, for example, the fire risk, so that you are predicting, okay, like now we have satellites measure these conditions that there is like a very high risk for fires. So that kind of information is available also before the fire. But of course, that kind of risk maps cannot say exactly if you are going to have a fire and where exactly do you have the fire.
Okay, well, thank you very much. It was a very interesting presentation. Thank you for answering the questions. We got a lot of them, so it shows that
Thank you.
it was super interesting. Thank you again. Okay, so I think I will now leave the floor to Daria, and I will actually show the right slide.
Thank you, Marine. So yeah, now we will pass to another presentation by Rosa, and she will talk about possible role of anthropogenic climate change in the record-breaking 2020 Lake Victoria floods. So Rosa, you are here. We can see you.
Yes,
and
hello.
Yeah, we can hear you as well. Okay, you can go.
Okay, well, hello, good morning, everybody, and thank you very much for inviting me to speak in this webinar. Today I'll be presenting a project that we published a couple of years ago, analyzing the floods that occurred in Lake Victoria in East Africa in 2020, using SAR-based flood mapping and using an extreme event attribution framework to study the possible role of climate change in this event. So the context was that between late 2019 and mid-2020, numerous flood events happened across East Africa, which according to UN estimates affected over 3 million people and caused hundreds of casualties across the region. And they also affected Lake Victoria, which is a large transboundary lake that is shared between Tanzania, Uganda, and Kenya. And lake levels rose very dramatically in this period, and there was flooding of tributary rivers and along the lake shorelines. Here you see some news reports from this period. So you see that a very heavy short rain season between October and December 2019 across the whole East Africa region. There was flash flooding, river flooding, and a rapid increase in the Lake Victoria levels, which garnered a lot of international media attention. The levels rose to such a point that in May 2020, they broke previous records since the late 1800s, and in particular, they broke the previous record that had occurred in 1964. And this, there was ensuing flooding of the lake shorelines, as I mentioned, and of tributary rivers, which displaced thousands of people that live around Lake Victoria. They also temporarily damaged the hydropower infrastructure at Jinja in Uganda at the outlet of Lake Victoria, and caused temporary power cuts. This all occurred in combination with a COVID outbreak and with locust infestation in the region. So it was a very high impact combination of events. And the displacement was very long lasting due to backflow effects from the high lake levels, meaning that people weren't able to return to their homes for months. So in some, I wanted to show you here, I mentioned already that the lake levels and the precipitation were record-breaking in 2020, and I wanted to show you the time series. So this is the time series of Lake Victoria's levels from the late 1800s to 2020, from a combination of in situ measurements at the dam in Uganda and satellite altimetry derived measurements from the Tahiti dataset. And you see that the 2020 levels broke the previous 1964 records by a relatively small margin, but nonetheless did break this record. And you see that the basin precipitation, so the precipitation over the whole Lake Victoria basin derived from the Persian CDR dataset, which is also satellite derived, was record-breaking in 2020 compared to all the previous years for which this dataset exists, which is from the early 1980s. And what we wanted to do in this study, and I've put the reference here if anybody wants to go look at it for more details, was first to determine what the spatial extent of the flood was and to estimate how many people were impacted by these floods, in particular around the Lake Victoria area. And we did this using a SAR-based flood mapping algorithm called HAZARD that I'll give more details on in a minute. And then we also wanted to analyze whether we could see a signal of climate change making these floods more likely or more intense. And we addressed this by carrying out an extreme event attribution study on the event and combining this with a water balance model designed for Lake Victoria. So based on inputs and output information, importantly, precipitation information over the basin, this water balance model simulates lake levels of Lake Victoria. So in a little bit more detail, what we did is that we used Sentinel-1 and Sentinel-2 imagery, in particular Sentinel-1 imagery, which is processed through the HAZARD flood detection algorithm. And this is able to produce a very high resolution flood map, multi-temporal flood map that we produced for the period for which the impacts were most intense and the lake levels were highest. And we combined this with high resolution gridded population data from the World Pop dataset in order to estimate what the spatial extent of the flood was and how many people were impacted. And then we turned to look also at lake levels. So we looked, as I mentioned, to a combination of in situ measurements and satellite altimetry derived measurements. And we also reproduced these lake levels using a water balance model forced with observational precipitation over the basin to see how well this water balance model could reproduce the 2020 peak event and the lake levels in general. And then we forced the water balance model with precipitation data coming from an ensemble of CMIP6 simulations, previously downscaled and bias adjusted within the ISIMIP project, in order to simulate lake levels with climate change and without climate change. And then combining these lake level sources with extreme value statistical analysis, we were able to address the question of whether climate change made these extreme lake levels that we saw in 2020 more likely or more intense. So in the first part of the study, we used SAR-based flood mapping tools. SAR stands for Synthetic Aperture Radar, and this is an active remote sensing system. And the instrument is available on Sentinel-1. We used imagery coming from Sentinel-1, the Sentinel-1 mission, which I know is available on through WEkEO. And SAR imagery is very useful for flood mapping because it can produce imagery in all weather conditions, including in cloudy conditions, and in day and night. This is because the instrument sends out a microwave radar signal towards the surface of the Earth, which can pass through clouds and which doesn't rely on visible light, so it doesn't need daylight conditions. And then part of this signal is reflected back from the surface of the Earth to the instrument, which can then make measurements based on the characteristics of the signal that is returned. So we analyzed this imagery using the HAZARD flood detection algorithm, and this is based on detecting a change in backscatter signal. So you see in the image to the right here that if the surface is very smooth, most of the signal that's emitted from the instrument will be reflected away from the instrument, and therefore very little of the signal will return to the instrument, and this area will appear as dark. Whereas if the surface is very rough, there will be a lot of backscatter, and more of the signal will return back to the instrument, and will therefore appear as relatively light in terms of SAR imagery. And so flood detection tools are generally based on detecting a change in backscatter signal. So from a situation of low backscatter and high surface roughness into a situation of higher backscatter and more surface smoothness, because built up areas and vegetated areas have a higher surface roughness, whereas water bodies are smoother. And so flooded areas appear as areas that have that experience a detection in backscatter. But the problem with this is, with applying this over large areas, is that this is based generally on choosing a threshold, a parametric threshold that represents a change, so a flood. And if you apply this over a very large area, you have a large dominance of pixels where no change has occurred. And therefore, the user needs to specify images that are relevant to detect the flood, which means that these tools can't be easily applied in an automatic and unsupervised way. So what Hazard does is that it applies a hierarchical split-based approach to select the best threshold, meaning that it takes the images, subsequent pairs of images from consecutive days, and it automatically splits these into smaller tiles until it finds a size of tile in which the balance between change and no change pixels allows it to determine a signal for the bimodality of the distribution, and therefore to effectively map the flood. This means that this algorithm can be applied over very large areas where no flood dominates to flood, and it can be applied with little supervision, so without the user needing to select the two images to compare. And I'd like to mention the Luxembourg Institute of Science and Technology that developed this algorithm, and the WASD cloud computing platform that I personally use to access the algorithm, which offers capabilities similar to WEkEO in terms of accessing in a cloud-based way the satellite data and the processing tools. So the results of this analysis I show here. So you see a map of the Lake Victoria and the areas that we identified as flooded through the automatic algorithm. The areas appear a little bit larger than they are for visibility because you see the outline of the identified areas. And you see areas that we found were particularly affected. So we focused on areas within the Lake Victoria Basin that were also located within 50 kilometers from the lake shores to focus on areas close to the lake. And we focused on the period between April and June 2020 because the peak lake levels occurred in May. And this was also the period in which news sources and reports of flooding reported the most flooding events. And we estimated that in total, approximately 650 kilometers squared were flooded within this area, affecting, when overlaying this with gridded population data on resident population, affecting an estimate of approximately 30,000 people. And I will now zoom into this region, so the Nzoia-Yala Basin in Kenya. And you see here an example of how we estimated the number of people affected. So you see the flood detected through the hazard algorithm overlain with the gridded population data, showing how we estimated the number of people that were affected by this flood event. I also mentioned that there is spurious flooding detected when, for example, there's wave conditions all over the lake. So we had to use a water body mask for the lake that I'm happy to discuss later. And here I wanted to show the difference between using hazard in its fully automatic way, so providing it with a 3-month window and asking it to compare consecutive pairs of images with user-specified dates of imagery. And you see that there is good agreement, but also some situations of disagreement in which the user-specified dates do identify more flooding, showing that visual analysis of the imagery is always useful. So as I mentioned, we estimated between April and the end of June, 650 kilometers squared to have flooded, affecting about 30,000 people. And we can compare this with other estimates from other institutions and government sources, although I have to premise that all of these estimates looked at slightly different time windows in different areas, so they cannot be compared like for like. But nonetheless, we can, for example, look at the Copernicus emergency management system that was activated on the 9th of May, 2020, and estimated 60 kilometers squared to have been flooded. But they looked at a much smaller time window than we did. We can also look at the MDAT database, which is a database on impacts from natural hazards. and which was activated between, it has a listing between April and the beginning of May 2020, but focusing exclusively on Ugandan impacts near Lake Victoria, and estimates that 200 people were affected with 5 casualties. There are a number of other MDAT listings, but that look much more broadly across East Africa. And if instead we look at news, disaster risk recovery, and government sources, we can compile these sources to an estimate of over 50,000 people affected in the surroundings of the Lake Victoria area in Uganda, Tanzania, and Kenya. So you can see a broad agreement in our estimate of people affected, in particular with this combination of news, disaster risk reduction, and government sources. Then in the second part of the study that I'll be a little bit briefer on because of the context of this webinar, we carried out an extreme event attribution study on the lake levels. So we defined the event as a rapid 180-day rate of change in lake levels. Between November and May, lake levels rose by 1.2 meters. We investigated the drivers of this rapid rise, and we modeled the probability of the occurrence of this rapid rise in levels with and without climate change, combining statistical modeling to model the non-stationarity of the time series with climate change, with lake level modeling to model the water balance components of the lake, and precipitation data coming from GCM simulations run with and without anthropogenic emissions. We saw that precipitation was above average in the basin between May 2019 and May 2020, meaning that both the short rains and the long rain season were above average. And we know that this is associated with a positive Indian Ocean dipole, which is known to cause heavier rainfall conditions in East Africa. Looking at the water balance terms of the lake, we saw that the precipitation over the lake, which is actually the dominant input term in the water balance of the lake, because the lake is so large, was above average, as was also the inflow from the basin into the lake, and that this was not balanced by an increase in the outflow, which is controlled at the dam in Jinja in Uganda. We then carried out an attribution to anthropogenic climate change based on this rapid 6-month rise in lake levels, and we estimated that it's today approximately a 63-year event. Our best estimate was that this was made approximately 1.8 times more likely in the present climate compared to a pre-industrial climate, but our confidence interval included the possibility of no change, so a probability ratio of 1, meaning no detectable change in likelihood. And looking at the change in intensity, we saw that an event with the same return period is estimated to be 7 centimeters more intense than it would have been without anthropogenic climate change. And 7 centimeters for a lake as large as Lake Victoria is equivalent to thousands of cubic meters of water. So our conclusions for this study was that this was a very high impact event, that the lake levels were record-breaking, that they were driven by above average over-lake precipitation and inflow into the lake. We estimated that today this was approximately a 63-year event, and found a possible role of climate change in increasing the likelihood of the event by 1.8 times and the intensity by 7 centimeters. But there's a relatively large uncertainty in our attribution statement due to high natural variability. We didn't explicitly look at the Indian Ocean dipole in our study, but we know that there's an important role of positive Indian Ocean dipole in increasing rainfall in East Africa, and other research has projected a future intensification of positive Indian Ocean dipole events with climate change. There are a number of factors that we didn't explicitly include in our study and that could be interesting for the future, including land management in the wetlands around the lake shores and upstream in the rivers, an explicit modeling of river flooding using hydrodynamic modeling, and mesoscale circulation. So Lake Victoria is very large, meaning that in some way it creates its own weather. And this is reproduced in kilometer scale convection permitting models, but not fully in global climate models as we used for our precipitation inputs. So with this, I'd like to conclude and thank you, and I'll be happy to take any questions.
Thank you, Rosa. It was a very nice presentation, and we indeed have some questions for you. So I'll share my screen to see them. I hope you see my screen. You do see it, right, Rosa? You can confirm? Okay.
Yes.
So the first question is, can you again tell how you calculated the spatial extent? Did you also use ESA Snap to pre-process the data?
Mm-hmm. So no, I didn't use ESA-Snap because I used Hazard through the WASD cloud computing platform. So it accesses Sentinel-1 data, but not through Snap. It does this directly through the Hazard algorithm. And we did this by focusing on locations within the basin and 50 kilometers from the lake shores, and carrying out an automated flood detection between April and June. So a multi-temporal flood map. So any pixel that was identified as flooded at least once during this window, we considered as a flooded pixel. And then we removed the lake itself. There was spurious flooding that was identified over the lake because of wavy wind in the lake, causing wavy conditions that then increased backscatter, and therefore there's a change detected by using the water body mask from COPDEM. And then from this multi-temporal flood map, therefore calculated the spatial extent of any pixel flooded at least once in this time window.
Okay, thank you. The next question is, how exactly can you estimate number of affected population using the hazard?
So we, based on this multi-temporal flood map that we constructed, we overlaid this with the resident population based on WorldPop data. So WorldPop is gridded population data that's available at 100-meter resolution. Hazard produces the flood map at 20 meters, so we assumed that within the 100-meter WorldPop resolution, the population was equally distributed, and in order to use the full high resolution capacity of the hazard and the Sentinel-1 data. And we estimated basically any person resident in a flooded area as affected.
Okay. Next question is it possible to use the hazard algorithm without masking the water bodies?
I think it's possible for smaller water bodies. The Lake Victoria, being very large, presented this problem with windy conditions. So over river bodies, for example, when hazard is used for river flooding, they don't mask the river. It's not necessary. But for Lake Victoria, it was necessary, which created a little bit of uncertainty in our mapping around the lake shores, because it depends on what reference time the water body mask was produced in.
Okay. Thank you for this answer. Can we learn from this use case to predict the floods in the future?
Well, I think that there's flood mapping tools like Hazard are very useful for monitoring and for emergency responses. And indeed, what we tried to do with the extreme event attribution was also to see if we could somehow estimate changes in the likelihood of these events. So every flood and situation is very specific, but I think indeed it can be useful. Although for prediction, of course, you might want to use more forecast data and models that can use forecast precipitation data.
Okay. And the next question is, does the lake level also correlate with tidal or sage activity? And are there any inexplicable observations you made?
That I know of, no, we didn't particularly look at this. And I'm not sure what you mean by inexplicable observations.
I guess they wanted to say that there's something you noticed and you don't know how to really explain it. Like you don't know what to attribute it to what.
Right. Yeah. So okay. So in terms of of windy conditions and changes in the short-term fluctuations in the lake, we looked over relatively long periods, so over 180 days. So very short fluctuations would be kind of masked out by this fact of looking over a 6-month period. And in terms of inexplicable observations, not really. I think there are many things that we could have explained and looked into more and more carefully more in the future. But no, I can't think of any surprising observations.
Okay. I think we can go to another question. Okay, so hello, thank you for your presentation. I know it's not the main focus, but could you explain the attribution part a bit more, how the change in intensity and probability ratio was obtained? Thank you.
Yeah, absolutely. So we applied a method for mixture event attribution. So this is based on finding non-stationarity in a time series that is correlated with global mean surface temperature, which is used as a proxy of global warming. So in the observational time series, the method basically identifies whether there's a trend in your time series that you're analyzing with respect to global mean surface temperature. And combines this then observational based line of evidence with line of evidence based on climate models, so that you don't have just the realization from the real world, but also the realizations from the climate models, and ideally from an ensemble of climate models that therefore includes model uncertainty, but also natural variability. And in these historical simulations, we again applied what they call a shift width methodology. So it's again finding this, whether there's a trend in the variable compared to global mean surface temperature. And we also applied this on HISNAT models, so GCMs where the anthropogenic emissions are removed, so that any trend that you find would be due to natural variability alone. And we found a trend detectable in observations and in historical simulations within a large uncertainty interval, but not in historical natural simulations. And the methodology then combines these line of evidence into a synthesis statement, which is what I showed in the slide. And the calculation of change in probability is based on identifying the intensity of the event in the observational, in the real world, and then finding events with the same return period in the models and seeing if that events with that intensity that was observed change in likelihood based on this estimation. And the change in intensity is done by fixing instead the probability of the event in the present day and seeing if events with that same return period change in intensity between present day climate and a pre-industrial climate.
Okay, thank you. So once again, we have more questions, but we don't have much time left. So thank you again, Rosa, for your presentation and for the answers to the questions. As Marine said before, the rest of the questions, we will send it to you so you can answer them, and then we can provide this information to participants. And now we are going to move to the next presentation. I will stop sharing my screen, and our next presentation is by Ben Loveday, and I'm just Ben, you are here. Okay, we can see you.
I am here. Thank you, Daria.
Yeah, great, and I can hear you. So yes, you can go on with your presentation.
Will do. I'll just share my screen. Let's see if this works okay. Should do. Okay, so please let me know if you can see that okay.
Yeah, we can see it, yes.
Fantastic. Well, good morning, afternoon, or evening, everyone, wherever you're joining from. My name is Ben Loveday, and I run the Copernicus Marine Training Service for EUMETSAT. So it's my job to support users in applications that use the marine data streams that EUMETSAT produce through Copernicus. So that's those that come from Sentinel-3 and Sentinel-6. In my slot today, I'm only going to be focusing on a demonstration of the use of various types of marine data for a given application, in this case around tropical cyclones and natural disasters. So I'm going to focus much more on how we can use the WEkEO system to explore data usage through Jupyter Lab and Python-based Jupyter notebooks, as opposed to any presentation. So I've got no presentation here, and I'm going to launch straight into doing a demonstration on how we can work with various data sets from altimetry, from sea surface temperature and tropical cyclone heat potential, and also from some external data sets that give us information on some well-known and well-characterized storms over the last few years. So I'm going to start, and you may have seen this before, but I'm just going to do a very short kind of revisit to how we actually get to the Jupyter notebooks and what's available on the WEkEO system. And then I'll show you how to set up and run one example, and at the end we'll take some questions. So I'm going to begin with at the WEkEO front page website. I'm already signed in here, so I'm just going to navigate to the Jupyter catalog to show you what's available and what notebooks we'll be working on today. So once I'm signed in, if I click on Services and Tools, I can immediately access all the various options that we can find on WEkEO, either to view data, to look at data that's available, or in my case, to go to the WEkEO workspace to work with some of the Jupyter notebooks that directly connect to the various data sets, in this case, marine data sets that are available on WEkEO. So if I click on the Jupyter catalog, hopefully this is updating as we go. So this should open a list or a roster of all the available notebooks that we have on the WEkEO system. And you can filter these, let me make this slightly bigger for you, to your particular thematic or variable or sensor or satellite platform of interest. And you'll see on the left-hand side here where we have listed theme, we have a load under atmosphere, under climate, and we actually have a huge number, about 107, on working with marine data on WEkEO. EUMETSAT are one of the supporting entities of the WEkEO system, and so all of the notebooks that I and my team write for working with data from Sentinel-3 and Sentinel-6 is available to use on the WEkEO system and connects to the data within WEkEO. So I'm just going to filter by marine, just to filter down this list of all the notebooks that are there. And the one that I'm interested in for today is using altimetry data. So that's data from the Sentinel-3 SRAL altimeter and from the Poseidon-4 altimeter on Sentinel-6. So I'm going to focus again by sensor. And that will leave me with 20 odd notebooks for me to scroll through. And some of them are focused on applications and some of them are focused on using data themselves. And we update these all the time. So feel free to check back in or message me if there's something specific you would like to see with regards to the use of altimetry, ocean color, or sea surface temperature data. And right towards the end, we have a new example called Monitoring Tropical Cyclone Intensification and Impacts. And that is the one that we are going to look at today. So I'm going to click on this example. And this will open up what we call a rendered version of this notebook. So it's a version that's already been pre-run, but gives you an idea of what the notebook actually looks like and how it's going to run. And from here, we can access the live version that we're going to play with today. So at the top here, you can see a small example picture, a brief description, and some tags that are associated with this notebook, giving us an idea of the types of data and variables that we're going to use. And then we have a rendered version of the notebook itself. I'm not going to go through this because we're going to actually go through this a little bit step by step in the main body of the demo itself. One important thing to remember is at the top here, if you click on Open via Jupyter, this will launch this notebook directly on the WEkEO Jupyter Lab. If you go to Open on GitLab, it will open the source code for this notebook, so you can clone this notebook to run in any circumstance you wish, on your local systems, on other remote systems. If I just click the Open on GitLab, this will take me to the WEkEO GitLab where this notebook exists. And this is in a repository here, for those that know Git, called Ocean Case Studies. And inside this repository is everything you need to run this notebook in any context you wish, including environment files and all supporting infrastructure you need to run it. I'll refer back to this again in a little bit, but for those that want to run in any other context, then you're more than welcome to do so. But it is already set up and supports running on WEkEO itself, so you can run it in the context of the WEkEO Jupyter Lab, should you wish, which is what we're going to do now. One important thing to point out is further down here, it gives you the instructions of how to get this notebook on your own system, so how you clone it via Git. So there is a line that's highlighted here, which I'm going to refer to in a minute, which is how you can git clone this notebook, all its dependencies and submodules onto any system. Okay, so going back to, to the WEkEO Jupyter catalog, if I click this Open via Jupyter button, this will then launch this notebook directly in WEkEO Jupyter Lab. So now this is a live version that's ready to run that you can choose to play with one small caveat. So when you click on these the Open via Jupyter button, it will open the notebook inside a file structure here that sits inside public and WEkEO for oceans. And then here are all the repositories that contain all the notebooks for marine, and the one we want is in ocean case studies. However, the ones that sit within this public folder are read-only, which means if we want to make any new data, we cannot run them in this space. So what I recommend you do is either copy this folder into your work folder, or as I've done here, just use that git clone command from a terminal to take a new copy and clone it directly into this space. This may be something that changes in the future, but at the moment, if we actually want to run a notebook where we adapt it and we update it and we make new plots, we have to move it to a space that's read-only. That protects the other, that we can write to. That protects the read-only ones from being overwritten. And it warns you up here that notebook is read-only. So in my version that I have, it is not read-only. So I'm going to close this one down. And here is my copy of my ocean case studies repository. And inside here, I have an index file. And this index file contains links to all of the other notebooks that are runnable on WEkEO that fit within this kind of case studies, this application-focused kind of context. And the one we want to look at, it's the same one as before, monitoring tropical cyclone intensification and impacts. And because I'm in this work folder, I'm not read-only anymore. I can run with this. So now we're at the kind of the gateway to working with this data. I'm going to remove all the extraneous stuff from the screen and make it a bit bigger so you can see what I'm doing. And we'll focus mostly on this application. So what are we actually going to do in this notebook? The goal of the notebook in general is to bring in data from multiple sources to focus on one specific storm example, though you can adapt it to others, and to look at some of the supporting marine data we have that shows or gives us an idea of why this tropical cyclone intensified in the way it did, and what caused it to grow in intensity as it passed over, in this case, the Gulf of Mexico, and what was the impact on the sea state from this tropical cyclone passing over the ocean surface. So we're going to bring in data from the NCEI IB tracks record, which gives us information on storm tracks. We're going to bring in tropical cyclone heat potential data from NOAA. They calculate this as their own product based on sea surface height and in situ data. We're going to derive our own tropical cyclone heat potential metric or variable from the Copernicus Marine Service Analysis and Forecast System. And we're also going to bring in altimetry data to look at significant wave height. And that altimetry data is taken from Sentinel-3 SRAL and Sentinel-6 Poseidon-4. And everything you need in order to authenticate for the systems that provide the data and or to understand some of the data you're using is explained in this prerequisites box at the top of the notebook. There are also links here, make this temporarily slightly smaller, links to the descriptions of every type of data that's used in this analysis. So if you want more information on the altimetry products or the Copernicus Marine Service sea surface height or analysis and forecast products, you can link to the descriptions here. The descriptions can be found either via the Copernicus Marine Service website or web portal, or on WEkEO itself. And there's also links out to the NOAA products that we're calling into scope as well. So what do we hope to learn from this? We hope to learn how to retrieve marine products either from the Copernicus system or from other systems, or Copernicus program, or from other systems, and bring them into context, accessing them either from the EUMETSAT data store or the Copernicus Marine Service data store. And we're going to plot them in combination with some other data sets from NOAA. And the reason why we care is that hurricanes, whilst being a fairly regular occurrence, a natural occurrence, have significant impacts on coastal and inland communities. Obviously, they cause widespread destruction, loss of human life, have enormous economic and social impacts. And we've noted, or has been kind of noticed recently, that the intensity of these might be increasing. And it's a very important forecasting and monitoring activity to be able to look at these storms and get an idea of what's happening both in the atmosphere and also in terms of the sea state, because that allows us to operationally respond and to give guidance to people on the ground to protect themselves and protect their assets. So it's a fairly common workflow that we develop and kind of demonstrate all the time. And in this case, we're going to look at a storm that hit the US in 2024 called Milton. You can adapt this notebook to look at any storm that sits in the IB-Trax record, but Milton is the one we'll focus on now because it was fairly widespread, quite devastating, hit in October 2024 and crashed into the Gulf of Mexico side of Florida, as we will see. So at the moment, for those that have not worked with Jupyter notebooks before, I should just clarify, there's two kinds of things on the screen that you'll see. There's the parts that are in the gray boxes, and they are live runnable code. And then by and large, there's everything else. And everything else is just decoration. It's either text or it's contextual imagery, or it's just a way of dressing up the code to make it look quite nice and to give us a way of building a narrative that we can follow, a story that we can follow through the application that we're looking at. And in the code blocks, if we have a little number here, that means that the code has already been pre-run. And we don't want it to be pre-run. We're going to run it here live. We're going to risk it. So I'm going to completely clear the notebook. So I'm going to restart from this kernel menu, restart and clear the output of all cells. And now all of these little kind of chevrons, brackets, whatever you call them, are empty. Code is completely clean and we can choose to run. When we run this code, we have to make sure that we activate the correct environment, or all of these dependencies that we need will not work. So in the top right-hand corner where it says WEkEO lab here, you have a choice of kernels. So the kernel is what loads the environment to run your code. You have to make sure that you've chosen the WEkEO lab environment in this case, and I've already chosen it. So it says WEkEO lab up here. Okay, so we're good to go. So with a bit of luck and cross fingers, I'm just going to hit Shift and Enter, run this cell, and all of the prerequisites that we need to run this code are now loaded. They are all at the top of the script in all cases with my code, so there's nothing else to import further down. Everything is now ready to go. And the first thing we're going to do is we're going to set up our analysis. So we're going to be working with this IB-Trax data set, and in order to pull out the correct storm, we need to give it the name of the storm. And also because the names are often used more than once, we need to give it the name of the year of the storm as well. So this is Storm Milton from 2024. Well, it's Tropical Cyclone Milton rather than Storm Milton because it reaches a fairly high category. Again, we'll visit that in a minute. And there are three options in this code. I'm going to run through one of them. You can either choose to work with gridded sea level anomaly data. So that tells us what the sea surface is, what the sea surface height change is from climatological mean or from MADT. We can work with tropical cyclone heat potential from the NOAA archive, which we just ingest as is, or we can derive our own tropical cyclone heat potential metric from the Copernicus Marine Service. I'll refer a bit to what tropical cyclone heat potential is in a bit. So I'm just going to run in that information. Now, we need to tell our code where to get the data from and what data to get. And so for our altimetry data, at the moment, we're going to work with data from Sentinel-3 SRAL and from Sentinel-6. And these are the level 2 altimetry products. I've already pre-downloaded these. It doesn't take very long to download them, maybe 3 or 4 minutes, but because we're like time bound to half an hour here, I've chosen to put this as false for the downloading. But if you look in the menu on the side here, let me just go to the correct notebook. It lives in maritime safety. I've already got this products Milton, so I've already downloaded all the altimetry products that I need for this analysis. It does not take very long. I've only done that just to speed up things. But in your case, if you're working with the code fresh, these will be tagged as true. So, okay, I've got all my data. NT just means I've gone for non-time critical data, so not the near real-time products, those that have been processed a bit more thoroughly and have slightly higher quality, because we're working with a storm from 2024, not one from recently. And in the window below here, all I've done, I'm going to skip through this very quickly, it's just parameters I use to control plotting. You don't, in practice, need to change any of these. It's just color bars and scales. Okay. I have a load of functions here that I'm just going to click through. Again, they all control plotting, except for the top one, which computes my tropical cyclone heat potential. I'm going to come back to that one in a minute, but it's just a load of functionality we're going to call more than once that I've buried in functions at the top that we don't really need to care about. So moving on, the first thing we need is a storm. So we're going to read in the IB tracks, the international best track data from NCEI, from NOAA in the US, which is a fairly comprehensive record of large storms that reach a given category over the past, I think it spans about the last 25 years, but someone please correct me if I'm wrong, and is usually relatively up to date. But in this case, we're working with a storm from 2024, so we know Milton will be there. So we're going to get the data, we're going to read it in, and we're going to say, okay, fair enough. Inside our X-array object, which we've just put our storm record into, we've got 315 storms. Let's narrow that down now to just pull out the storm that we want, which is Milton, which is the one we specified earlier in the notebook. So we give it the name, we give it the year, we filter it down, so we've only got the data that we want, or the information that we want on this storm. And then we're going to pull out this information, and we're going to bear in mind this for later, that the storm is going to be categorized according to this Saffir-Sampson category. So anywhere from a tropical depression, which doesn't always actually even feature in the IB Tracks record, up to category 5 and above, which is a hurricane category. So Milton reached hurricane category, and we'll see that a little bit later on. So let's now just calculate a couple of small support variables. We're going to just calculate a rough radius to give us an idea on a map of how big the storm's effect, at least of the storm itself, not the full extent of the effect of it, but just the actual part that qualifies as the storm. And then we're going to look very quickly at the track of this storm. So here is Milton. Milton started here in the Gulf of Mexico on the 4th of October. And then spend quite a lot of time intensifying over the Gulf before hitting the inshore or the Gulf side of Florida, and then moving out into the Atlantic and then dissipating. So we have a 7-day window here, so a relatively fast storm generation and transit. And we're going to look at the reasons why it intensified in the Gulf, and then what happened to the sea surface state while it was passing over. So now that we've got our storm, we're going to go and get all the supporting data that we want to look at various ocean variables around it. So we're going to just query our storm and say, okay, what was the minimum and maximum spatial extent and temporal extent? And so we know we want to get data both from the Copernicus Marine Service, from NOAA, or from the EUMETSAT data store that falls within this spatial box, which is west, east, south, north over the Gulf of Mexico and southern and mid-latitude North Atlantic. And then we also want to get it over these days. And we've padded the days slightly, so we make sure we get products plus and minus 1 day either side of the storm. Okay, so we have a choice, as I said before, of what data we're going to get. But if we want to get data from the Copernicus Marine Service, we need to authenticate that service. So this part of the notebook actually tells you how you actually authenticate, and will set up how you add your credentials so that you can go and retrieve data from the service. And we have to do the same thing for the EUMETSAT data store a little later on. You can do this through WEkEO as well, through the WEkEO HDA, but in this case, I've done it via the other services. I may update this notebook in the future, so it just uses WEkEO. All will run fine here. And I want it to run the Copernicus Marine Service CMEMS, TCHP CMEMS, Tropical Cyclone Heat Potential from CMEMS workflow. So it's actually gone through and it's already authenticated me now because I have a pre-existing credentials file. If I didn't, then it would prompt me to create one. Okay, we're not using SLA, so that doesn't matter. And we're not using NOAA. Now, the key part of this analysis is in the tropical cyclone heat potential. So hurricanes and tropical cyclones are driven by ocean heat. And tropical cyclone heat potential is one measure of this heat, and what it does in terms of a definition, or what it is it's an integral of the heat in the ocean in the layers above the 26-degree isotherm. So when the ocean is warmer than 26 degrees C, we integrate all of that heat content in the upper ocean, and that is energy that contributes towards the intensification of a storm. So tropical cyclone heat potential gives us an idea or a measure of how likely a hurricane or a storm is to intensify once it goes over a given water mass. So we can get this data directly from NOAA, or we can calculate it ourselves. And one of the functions I've put in this notebook does the actual calculation itself. It's built for speed. It's not built for accuracy. So there's no interpolation in this TCHP calculation. But I encourage you to take a look and see what you think of the methodology. It's relatively simple, but there is some subtlety, especially when you get things like shallow areas or bathymetric shoaling towards the coasts, or you have a fairly sharp stratification in your ocean layer, and like here, I've not done any interpolation in the vertical. So it's a rough estimate, but it's good for our purposes now. Okay, so I'm going to go away and get the data that I need. So I'm connected to the Copernicus Marine Service, and it should say I'm going to connect, and we should see a little update here, and it should fetch the data that I'm after. Just give it a second to do so. And oh, there we go. So now I have my Copernicus Marine Service data already downloaded. In actual fact, you can work with the data directly. You don't need to download it. You can connect to the Copernicus Marine Service data store and work with the data on the fly. But for calculation of variables like tropical cyclone heat potential, that's actually slightly tricky, as you need to do lots of analysis, very small analysis on individual pixels. So it actually makes more sense to download it in this case. In many other cases, you can just work straight with the data in memory. Okay, so calculate tropical cyclone heat potential, done. Okay, so now we have our storm data, we have our tropical cyclone heat potential data for our time of interest. The last part of the puzzle is to get the altimetry data from the EUMETSAT data store. And that's what this part of the notebook does. So again, we're going to get any level 2 altimetry swaths. So this is not a gridded product. This is the single sensor product in a thin line called a swath or a track over a series of strips that fall over our spatial area in our given time. And these will get directly from the EUMETSAT data store. So as above, I'm just authenticating myself for the EUMETSAT data store. This works the same way as the Copernicus Marine Service little widget above. If you have a credentials file, it will automatically load it. If you don't have one, it will prompt you to create it. You will need, in both cases, for the Copernicus Marine Service and the EUMETSAT data store, to sign up for accounts and have your credentials ready to enter into this notebook. Okay, connect to the data store and let's see what collections are available in the EUMETSAT data store for the altimetry. This is going to go through and tell us only everything that is available for SRAL, that is the altimeter aboard Sentinel-3, which EUMETSAT processes in the marine domain. And it will return me a number of different collections based on the level of the data I want, which can be level 1A, B, or level 2, and also whether or not it's an operational collection or a reprocessed collection. For Sentinel-3, we are working with the operational collection because there is no reprocessing that covers 2024. There will be one shortly. And for Sentinel-6, we'll work with a reprocessed collection because we've reprocessed the data very recently that spans this time. And you should always, 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 if it's available, work with the reprocessed data because it is much higher quality. Okay, so I've doing the same thing for Sentinel-6 and Sentinel-3. All I'm doing is isolating the products and downloading them if I need to. But remember, I set the notebook for false for now just to speed up our time slightly. Okay, I've got everything I need. Now I'm going to gather all of these local products that I need, the level 2 ones, and put them into one master list of products. And now I have everything ready to run my final analysis and make my final plots of my storm track and my analysis of what is happening around the storm, both in terms of ocean temperature, tropical cyclone heat potential, and what is happening in terms of the significant wave height, which we will calculate from the altimetry. And this is going to make an animation. And this is the last cell, really, that I'm going to run in this notebook. And this is the one that brings all the information together. For every day, it will give you the surface field, which is the tropical cyclone heat potential. It will overlay the storm track and the history of that track. And it will then plot the swaths, the individual tracks for the altimetry for the significant wave height, all encompassed within that single day. So you can get an idea of everything that's happening. And it will run through this. I think there's about 40 odd panels. And I can show you while this is running what an individual panel looks like. So there's output Milton here. And make you a bit smaller so you can see. So here is the first example we have. Make it smaller again. Yep. Hopefully that's still the main part of it readable for you. So on this panel, we can see that we have this tropical cyclone heat potential in the red, yellow, blue. So we can see these areas of red associated with high TCHP, meaning where chances are, or highly likely, that we're injecting energy into the storm, whereas the blue areas would be more likely to remove energy from the storm or contribute less. We have this circle, which is the storm itself, its initial track and radius, and this color maps to the Saffir-Simpson hurricane category. So here we can see we're only category 1 really here. So this is the generation of the storm. This is where it kind of span up. It's not particularly strong or particularly extensive at this time. And we can actually see the reflected in this track here, which is from Sentinel-6, that there's not really much effect on the significant wave height around that storm kind of like genesis period. Now, just going to pop back and see how my notebook is doing. Because you should be getting towards done. So it's gone through every single day. And we're at the end. And the last thing we're going to do is from this storm, or from these animation kind of panels, we're going to make an animation. Now, I made the animation as a GIF because I was having some problems with generating an MP4 for this, though it is quite doable. And here we can see the final output, the evolving tropical cyclone heat potential field. And as the storm moves into these areas that are much, much darker red, we can see it intensifies, moves to yellow, reaches category 4 and category 5. And then it heads towards the coast of Florida, loses a bit of energy when it hits the coastal domain, where it's not quite, the tropical cyclone heat potential isn't so high, and is not gaining much energy, and then decays rapidly when it moves over the actual landmass, where it can't draw the heat energy it needs to sustain itself from the ocean. And as this evolves over here, we can see that we start to get some storm tracks along the coast of Florida, where the ocean surface is being driven towards the coast, and we get these very, very high waves, so significant wave heights of, I think, 8 to 10 meters along the coast, as the ocean is pushed forward in front of the hurricane and generates these rather large kind of storm-like conditions, which also are affected and contribute to storm surges and property loss and significant damage on the inshore or the Gulf of Mexico side of Florida. So we had very few waves generated on the western side of the basin, and towards the east we can see the intensification is relatively strong. So this is one example we have here, and I have other examples that you can run in this notebook of looking at the sea level anomaly or the tropical cyclone heat potential analysis from the NOAA product, not the Copernicus Marine Service product. And you can adapt this analysis to look at any storm that's in the IB-Trax record. So if you want to look at Hurricane Freddy or Hinamnor in the Indian Ocean in the last few years, or any of the large storms, though not cyclones, that occurred in the northeastern Atlantic in the past year or in the past 2 years, then you can adapt this notebooks to do so. And yeah, so I think that's the end of my demonstration here. You should be able to run this relatively easily straight out the gate, as long as you activate that WEkEO lab kernel and authenticate yourself for the services, then there should be no barrier to you running this. And if you encounter any issues, the last thing I will say at the bottom of the notebook is there is some guidance for how you contact us with regards to support on this notebook. If you're having any problems running it, if you have ideas for future notebooks that you want to see run with different examples of marine data usage, ocean color, sea surface temperature, or altimetry, then please contact us and we'd be happy to develop it. So I'll leave that there for now. Thank you very much.
Thank you, Ben. That was a great presentation, very detailed. And we've got 2 questions for you. And I think one of them you basically already responded to. I will start sharing my screen. Let me know if you can see it. Is it good?
I can see, yes.
Yeah, great. So we have a couple of questions. So first one is, the notebook looks amazing. Is there a similar version for tornado analysis? And is the altimetry also suitable for mesoscale events?
So it's an interesting question, and the first thing I would say is my focus is entirely marine. So I've not looked at tornadoes at all. If you're and your second part of your question, is altimetry suitable for mesoscale events? If you're talking about analysis of mesoscale convective systems from a weather perspective, then altimetry can give you some idea of how the sea surface is being affected by those systems. If you're talking about the mesoscale ocean, so eddies, currents, filaments, the altimetry is highly suitable. In fact, altimetry is probably one of the major techniques we use to analyze the movement of the ocean in the mesoscale. And it's certainly the only one where we can really get a global picture of mesoscale variability of the ocean.
Okay, thank you. For the next question is, hello, Ben. I'm interested in applying your code to my study case. If I face any error in the future, how can I ask for help? Well, you already said, like,
just fine. Click on the buttons at the bottom, or there's information on the READMEs for all the repositories for how you reach out to us and ask questions. I have authored pretty much all of these, so it'll almost certainly come to me, and I'd be happy to help.
Great. And the last question, is it easy to move a whole analysis to Anaconda?
Yeah, it's built for Anaconda primarily.
Okay.
You'll find in the repository full instructions for how to set this up on Anaconda, either Miniconda or full Anaconda Navigator on any OS. So yeah, you should be able to do it, no problem.
Okay, great. Thank you. We have another question that just came. Is it possible also to analyze other disasters?
Other disasters? Yeah, so we've done some analysis, though it's quite subtle in tsunami detection. We've done lots of analysis with regards to biogeochemical natural disasters in the form of harmful algal blooms, large river outflows, some analysis of detection of underwater volcano eruptions if they feature on the surface. So yeah, there's a broad spectrum of disasters. We've focused a lot on marine heat waves, if you count those as natural disasters. I think probably most people would now. So yeah, just please have a look through the catalogue and see what you can find. If there are any ones we've missed, then let us know.
Great. Well, thank you. Thank you again for your presentation and for your answers. We don't have questions for you. Like, we're not gonna send you more questions to answer like after the event. So that's it. And for now, we are moving to the last part of our webinar, and it's gonna be Marine who's gonna tell some last words. Marine.
Yes, hi. So I'm gonna share my screen again.
Yeah, I stopped screen. Yeah, okay.
Okay. So yeah, I'm just going to steal 5 minutes of your time to give you some details about some elements of this webinar. So thank you very much to all our speakers from today and for answering all the questions we received from participants. Thank you to everyone who asked questions as well. This really makes our sessions quite interactive, so that's really good. We hope you got a better understanding of what is WEkEO, what data is available through the platform, and how it's being used in real life. Part 2 of this training session will happen this Thursday from 10 a.m. CET. We will show you how to access and download data from the WEkEO viewer, and we will go through the demo of 3 tutorials using Python, R, and QGIS. These tutorials are already available on the tutorials tab of the event website, so feel free to have a look before Thursday. You'll also find replays and polls on the event website through the menu at the top of the page. We will send you an email to let you know when the replay is available and a link to the poll about today's webinar. You will also receive a certificate of attendance after day 2 of this training session, so after Thursday. And if you'd like to go further, after today's session, I encourage you to visit the WEkEO YouTube channel, where you'll find a rich library of webinars and training sessions from the past few years. They're all freely available. Each video focuses on a specific topic related to Earth observation, like ice monitoring or coastal interactions. It's a great way to deepen your knowledge at your own pace and explore use cases that match your interests as well. You can also find out about all the WEkEO events, both upcoming and past, via the Events tab in the top right menu of the WEkEO website. where you can open any event page for details and registration. So that's it for today. Thank you all for joining today's session. We hope you find the presentations useful and that you have a better understanding of how WEkEO can support the study and response to natural disasters. We'll continue exploring this topic during day 2 of this event. Have a great rest of your day and see you on Thursday. Bye-bye.